So I'm Lyman Page. I'm in the Department of Physics at Princeton University, and I work on a few different things, but my main research is on this radiation that's left over from the Big Bang that suffuses the universe, and it's called the cosmic microwave background. And it is microwave radiation, right? So the wave, unlike, say you study in chemistry, you study light from reactions and things like that. So those wavelengths are about of order half a micron, half of a millionth of a meter. Our wavelengths are sort of millimeter to a few millimeters size, so much longer wavelengths of radiation. So we still study a lot of the same fundamental things, but in the wavelengths that your eyes aren't sensitive to.
Yeah, that's really cool. I remember learning we had one unit about microwaves and radiation and just the light spectrum.
Yeah, cool. Electromagnetic spectrum. The visible part is one tiny little bit of that huge spectrum, right?
And then how did you get interested in research in the first place?
Boy, the first place, no, I was thinking about your email. I was probably curious about nature, always have been. I think probably the big jump came for me in college. So I started out as a philosophy major and then sort of philosophy English major. And then I took a course in physics and I just loved it. It just made sense. I was always okay in math, and so that helped. I just took a course in physics and I loved it. And so went to a library, looked for books on physics. Back when, you could just go browse libraries for books on physics, and just picked books out and started reading about cosmology and Einstein's theories and things like that.
And then in understandable terms to a high schooler, could you give me a quick overview of your research?
Sort of here's the nuts and bolts of what we do. Or you know what a TV satellite dish is? You've seen them on houses. They're just little parabolic, usually fiberglass dishes that are pointing up, and they receive transmissions from satellites in the microwave regime.
Oh yeah, I've
Like
seen.
little telescopes. Yeah, you see, some are small. They're mounted in the corner or something like that. They're pointing out. Okay, that's near the wavelengths of light that we look at. We look at a little bit smaller, but it's near there. So we take those and we point them up at the sky. Probably the best known experiment we did is we took some of those, not exactly because we have to be much more careful with the design, but we took those and put them on a satellite. And then at the receiving end, we put very sensitive microwave receivers. And so if you looked through, binoculars and you looked out and you saw something in the distance, right? And it's imaged down on your eyes. We took those microwave telescopes and looked out and imaged it down on our detectors and scanned the whole sky. What we did is map the whole sky, everything up. Satellite goes around, so we just mapped the whole, for us it went around the sun, but we just mapped the whole sky and made a picture of the cosmos in microwaves. Okay, so it's just like, if you look up at the night and you see the night, there are all sorts of, you see stars, and I know from Los Angeles, but you get out, you get a little ways away and you see stars and dust clouds and things like that. But that's invisible light. We mapped in microwaves. And then it turns out that the thing we're mapping, it's called the cosmic microwave background, which is radiation that's left over from the Big Bang. But it's now very cool, if you will, so it glows in microwaves. So we looked out at this radiation that's left over from the Big Bang by using microwave telescopes and made images of it, took pictures of it, like you would do, with the Hubble Space Telescope or the James Webb Space Telescope or something like that, except in the microwaves. And it turns out from those images, we could figure out all kinds of stuff about the universe, like how old it is, its composition, like what fraction is the stuff of which we're made, what fraction is another kind of matter, what's called so-called dark matter, what fraction is a cosmological constant, which is it's like a vacuum energy, and the processes that led to the.
Yeah, that's so interesting. When you're taking the picture with the microwaves,
Mhm.
how do you determine the scope? So are you just mapping our solar system, or are you looking further than that?
Way, 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 way further. Okay, so the light from the sun takes 8 minutes to get to us. Okay, right? If the sun went out, we wouldn't know it for 8 minutes, right? Because
Yeah.
light has a finite rate, has a finite speed. So 3 times 10 to the 8 meters per second, or 186,000 miles per second, right? So light has a finite speed. So if the sun went out, we wouldn't know it for 8 minutes. If you looked at I don't know how much, but if you like, here's the sun, the center of where the nearest star is Proxima Centauri, and it is around 4 light years away. So if it went out, we wouldn't know it for 4 light years. Okay, so that's just the nearest star. So the distances are enormous. And so then we get a star group. And then if you've seen the Milky Way, like out
Yeah.
of, okay, so that's our galaxy, right? About 100 billion stars in that. And the Milky Way to us has a center. So if you were in the center of the Milky Way, that is 25,000, roughly 25,000 light years away. And that's just our Milky Way. Okay. And we look way beyond that. We look in terms of light years around 40 billion light years away. So this microwave light, it really comes from the very furthest reaches of the universe that we can ever hope to see in light, but in microwaves. So we're looking way, 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 way out, so far out that it's so far back in time that we see the universe as it was when it was very, very, very young. So right now it's about 13.8 billion years old. We look out a little further than that because the universe expands while we're looking, but we look way, way, way out and really, really, really long time ago.
Yeah, that's so cool.
But
And then what were some of your most significant findings or publications?
the one people mostly point at was one where we figured out in a very tight sense what's called the standard model of cosmology. So cosmology is the study of the large scale structure in the universe. It's basically what's the big picture? That's what we're after, right? What's the universe made of, and how do those different components interact? How do they work with each other to make the universe we see? Through these measurements, we could figure out all the components of that model. So we could figure out the number of, quote, parameters that it takes to describe the universe, and then the basic processes that those parameters worked with, if you will, to form what we see today. So that was probably our big paper. And when you get to that scale, it's so simple. The Earth is very complicated, beautiful, of course, but complicated. But the cosmos can be described very, very, very simply. And if you think about looking as far back as you can, it was much simpler. And then as you get closer and closer to us, lots and lots more things happen, and you can see it gets more complex, more varied, and we're still understanding that is probably the best way to say it. But the furthest reaches, I'm sure we don't understand everything about it by a long shot. We understand a lot. So that's, I think, the biggest thing
Yeah, okay.
No, other things, we figured out the geometry of the universe has a geometry, age, composition, just things like that.
Yeah, that's so cool. It's crazy to me that you can figure out like the geometry of the universe.
Yeah, it's wild, isn't it? But it's as simple as, if you drew a triangle on a beach ball, so you come down one seam and then you say go around the equator and you go back and you sum up the angles for all those corners, right? They greater than 180 degrees. But if you draw a triangle on a piece of paper, any triangle on a piece of paper, and you sum up the angles, those equal 180 degrees. And if you were to go on a horse's saddle, say, and draw a triangle, just draw a triangle on a horse's saddle, those would sum up to be less than 180 degrees. And so in crude terms, what we do is use the cosmos and figure out where things are and sum up the angles. So we can see that in the geometric sense, the cosmos looks like a flat, to the best of our ability to measure, it looks like a flat piece of paper, not curved, or not like a horse's saddle or something like that.
Yeah, that's so cool. I feel like I always envisioned like the universe as a sphere, but it's like that's really cool.
Yeah, what we access is a sphere. So what we see and how we think of it around us is a different question than what is the geometry. Because let's say you're inside that sphere. if you pick any 3 points in there, if you go from your computer to the far corner of the room, to the other corner of the room, to back to your computer, you sum up those angles and they're 180 degrees. It
Yeah.
doesn't matter whether you go from your computer to down to the end of the street to the other end of the street and back, those are 180 degrees. Or if you go from here to the sun to, it's a little complicated, to the sun, to the center of the galaxy and back, those are roughly 180 degrees.
And then what were some of the biggest challenges that you faced in research and how did you overcome them?
Well, first, it's research, right? So bad things always happen. Things break. Like we build lots of stuff, and then we analyze the data from it. So things break, and you just buck up and soldier on and fix them and figure out what's wrong and figure out how to get around it. So teaching is always fun, right? Because you're always working with students. But research is there are just these incredible highs and these incredible lows when something breaks, right? And the lows can be long. You can be in a lull for a year or more, right? You just have to keep thinking about, what are you trying to figure out? Why are you doing it? Why are you doing it this way? You can have lulls for a long time, but you just think about how to make things better and work at it. Get back to the highs again, and all the fun, the more fun part. But no, I mean, the process is great. The highs are really high and the lows are pretty low. I mean, in this experiment I'm working on right now, one of our cryostats just got broken, which is, we cool these detectors down to 60 thousandths of a degree above absolute zero to make them super sensitive. And one of our cryostats just broke, which just means it'll set us back 3 or 4 months or something like that. Lots of money. PhD experiment was on a balloon because the receivers we build are really sensitive to water moisture. We either go to, say, the Antarctic or a satellite or a mountaintop in Chile or a balloon, which gets you above the atmosphere. So the thing I'd worked on for 5 years went up in the balloon and the balloon burst and it came down. I had a parachute, but the parachute made the landing not incredibly bad, but it landed and it was at night. And so we couldn't get to it. So the wind picked up the parachute and it just dragged it across this old cornfield. So anyway, so it took us a year to fix that, for example. But
Oh, thanks.
soldier on.
I don't know if I could just spring back up after that.
Yeah, well, it takes a little while. Yeah, spring. Yeah, but you got it though, right? You've got to overcome defeat. So it's important to build on it, learn from your mistakes and move on.
Yeah, okay. And then where do you see your research field expanding to? So what are some interesting topics that can be further explored within the next 5 or 10 years?
Yeah, so we're looking in two sort of separate areas. One is, have you heard about the LIGO experiment?
No.
No, okay. So this is an experiment that directly measured gravitational waves. So other people had seen indications of them, but this directly measured gravitational waves from two black holes circling each other. And what a gravitational wave is, it's different. You probably, when you did your electromagnetic spectrum, that is an electric field oscillating up and down in space, traveling at the speed of light, say, towards you, but it's up and down, oscillating up and down. A gravitational wave, say, going towards you, it's different. It squeezes space like this and expands space like this and squeezes space and expands space and squeezes it. And these waves are going through you right now, but the amount that you're being squeezed is incredibly small, way smaller than an atom, right? It's just you don't feel it, but on a large scale they exist. And the question is, we know they come from spiraling black holes. Do any of these waves come out of the Big Bang? So we're trying to figure that out. In which case you could sort of think of them as squeezing the universe. It's the whole observable universe. So that's one question. And then another question we're going after, and this is in a laboratory measurement, is that most of the matter in the universe, we know it's there because we can see it gravitationally, but we have no idea what it is. It's wild, right? So only 1/6 of the total amount of matter is familiar to us. So it's like if you looked up and you saw a planet orbiting, right? Just going around a circle. You know, by the law of gravity, there has to be something pulling it in to make it go in a circle. But it's like you see the planet orbiting and you look to try to see what's pulling it in, and there's nothing there. You cannot find what's there. And people have been looking for decades. You sort of see, you don't see it in planets, but you see it in larger scales, and no one knows what it is that's pulling that, say, planet in. So there are lots of hypotheses, and there have been lots and lots of checks. It's called the dark matter. So we know it has to be there because, in effect, we see those planets orbiting like nothing, but something has to be there. And there are lots of possibilities. The possibilities everyone thought were sort of sure bets 30 years ago aren't. They don't work. So it's one of the grand mysteries in physics. Anyway, there's one possibility we're particularly excited about. And so we're building an experiment to look for it.
Yeah, that's so cool. And then how did you find your passion for physics? And how would you like suggest a high schooler try to find their own passion for research?
Yeah, I mean, I found mine just from taking a class. You know, being open, I think I would have never, if you'd asked me what I was going to do in college when I walked in, I would have never said physics. If you asked me what I was going to do in high school, I would have never said physics. It was just sort of recognizing that, oh no, I really like this. And then not letting other things get in the way. I didn't even know if I didn't even really care if there was a career in physics. I just know I loved it, and I wanted to understand it more and make sense of it, try to understand it more deeply. You know, it turned out all right. Here I am. But I'd say that can be true for anything art. You know, people just all of a sudden they can't not do it, right? Or writing, or music, or biology, and any of the sciences, or any pursuit like that that just captures your imagination. And I think it's to listen to your mind when it's telling you this is really cool. Right? Like you said, you like chemistry. You know, there's so many cool things in chemistry, right? You don't just blow it off. It's just, okay, let's figure this out, the next step, and don't rely on being spoon fed. I mean, that means you're not really that interested. You've got to want to seek it out. Go to chemistry fair, look for biology, right? Look around in nature, see what's neat. A passion for it definitely helps. I think all of my colleagues share that. We just want to know, we just want to find out, figure out our section of the universe a little better, or our section of the world.
Yeah, okay. And then what traits do you think define a great researcher in their field? And what type of traits would you look for in like a potential lab member?
Well, curiosity is huge. If you're doing experimental work, ability to work with your hands. Sometimes we have analysis projects, we have lab projects, and people these days work less with their hands than they used to. But, just like, do you work on your bicycle? Do you have hand-eye coordination? That's a big thing. And I think it's true in lots of the sciences that's necessary. Or how's your math? And how are you relating math to the world around you? Those are all the sorts of things. Oh, and coupled with, enthusiasm for understanding the natural world. It's endlessly fascinating, and those sorts of things. So, when we interview candidates, we just talk with them, see what makes them tick, and look at their papers and look at what they've worked on, their last projects and things like that. There's no magic formula or anything like that. Curiosity is a huge thing, and a huge element. And you can sort of tell, right, if you're talking with somebody and they're curious, interested, and engaged. Do science. It has to come from you inside, right? At some point, you get handed projects early on to get you started, but that stops, and then it's all you, right? You have to be curious enough to think about the interesting problems and what grabs you. And it's not like, I want to be famous and think about this. It's no, I'm just curious about this, and I want to figure it out. So those traits, maybe soft traits, if you will. If you say you're analyzing data, you can look at tons of data, but if you are not of a mind to ask at every step, how do these fit together? How do they make sense? How do they relate to, say, in my case, physics? How do they relate to what we know about the physical world? If you're not doing that all the time, you're not making progress, right? It's got to be, that's what we do. That's what we all do.
Yeah, okay.
So
And then just for our final question, what type of tips would you give to a high schooler who's looking to go into like physics research?
stay with math. You won't do physics without math. So we had three boys, and but every one of them, even all through college, just math. Take math. If you want to do physics, just stay good in math. Go to museums and just think about the natural world and see if it grabs you. And there's so many things on the web that you can look at. For example, just stay curious, stay interested. Look for what rings your bells, right? Look for what piques your curiosity and go for it. And it doesn't have to be like the hottest physics problem or anything like that. Just, what we look for, say, and so this isn't, obviously isn't high school, it's not college, but in graduate school, probably the most important trait we look for is any evidence of independence in research. Yeah, you should do well in courses, all that kind of stuff, but that's completely secondary, right? You are thinking about nature. So it's that, again, that curiosity, and you are taking action to make sense of it. It's doing research, and it's surprising how it's so easy to say and how it's disconnected from many people. So it's that hunger, all those sorts of things. So just stay interested, stay engaged, take math, take science, all that sort of thing. English and the arts too, because that'll help.